I completed the basic rough geometry of the main plate in the last video, so the next step is to machine the slots used to locate the 3 clamps. These clamps need to hold the work so that turning operations can be centered anywhere within the diameter of the watch movement. There are a number of different patterns of slots, but one of the most common is the one shown here, with a single straight slot in the center and 2 curved slots symmetrically either side. An example of this pattern is the Bowley faceplate included with a Watchmakers Lathe iron box last week. How the center of the slots is defined varies, so I haven't been able to find any specific description of the advantages of the different arrangements, so I've based my own design on geometry that's practical to machine. The central slot is easiest as the only defining constraints are the line goes through the center of the plate and the end point distances. The end closest to the center is constrained by the closest practical distance to the central spindle, leaving room for the thumb screws. The distance to the circumference is only constrained by the need to leave enough material to ensure the plate is strong and stiff enough. The straight central slot will be the first operation, but I'm also leaving room to spot and center drill the 3 round holes defined in the schematic. Once I've defined these 4 features, all other operations will be relative to them, so they should be straightforward to set up. I'm using an edge finder to locate the center of the plate as defined by the existing hole. This isn't perfectly central relative to the current edge, but the edge has more cleaning up to be done once it is mounted on the spindle, so the hole is the best reference for now. The edge finder is a really snug fit in the hole, which means I have to be fairly close to the centre to start with, and finding the right point on the curve is fiddly. I need an edge finder with a smaller end or a proper conical centre finder. The distance from the end of the slot to the outer edge isn't a critical dimension, so I'm just marking it roughly with a Sharpie. The distance of the other end from the centre is a much more critical dimension, but without a DRO I have to rely on the dial to measure it. The lead screw pitch is 1.5mm, so measuring out 30mm takes more mental arithmetic than I prefer. I'd like to build an improvised DRO scale from a modified pair of calipers as has been featured on many other channels, but that's a project for another day. I'm being careful setting up the cutter for the first pass. I broke my previous 4mm carbide end mill doing overly aggressive plunge cuts with similar material, and this is the only suitable cutter I have left. I wasted a lot of time on scratch passes with inconsistent results before I realised my obvious mistake. I forgot to tighten the collet, so I've just been pushing the tool further into the spindle rather than into the part. I'm running the spindle at 1500 RPM. The cheap carbide cutter didn't come with any cutting speed data or a brand name I could look up, so I had to depend on what I could find on similar cutters from name brands. At 4mm diameter, the cutting speed is only 19 meters per minute, which seems slow for carbide, but this is almost as fast as my mill can do. Let me know if you have any cutting speed advice for small diameter cutters on a tiny milling machine. The smallest collet included with the mill is 6mm, and it seems to be specific to this mill, so I haven't been able to source any smaller compatible collets. 4mm end mills with 6mm shanks are rare, so I bought a straight shank end mill, turned an adapter from silver steel and brazed it onto the cutter shank. To get the best possible concentricity, I then mounted the cutter in a lathe collet by its original diameter and turned the outer diameter of the adapter down to size. Let me know if I should make a video next time I do the same thing. I started out with a 0.1mm depth of cut and lots of chatter during the plunge cuts. As the slot got deeper, the plunge cuts got easier as the cutting oil was contained around the cutter. I increased the depth to 0.2mm and finally to 0.25. I attempted one cut at 0.3mm, but the chatter increased dramatically, so I didn't try that again. Finally through. I'm done with milling for now, let's go back to the lathe. In part 3 I had a lot of trouble with chatter while turning down the outer diameter of the faceplate spindle in the 4-jaw chuck. The chuck is heavy, protrudes a long way from the headstock, and seems to have a few problems with heavier parts that protrude further. I've switched back to the stock 3-jaw chuck as the dimensions for the rough turning aren't critical. This part is destined to be mounted directly on the headstock, so I can do that final dimensions once it can be mounted that way. The 3-jaw chuck is smaller, lighter, and doesn't protrude nearly as much. The part is already centre drilled, but I need to re-drill the taper for the live centre as it isn't exactly centred for the 3-jaw chuck. The first pass is a little noisy, but that's mostly bringing the diameter into concentricity for the new mounting and dealing with the chattered surface from the previous cuts. Once the cuts are uninterrupted, it gets a lot smoother and cleaner. The lathe doesn't have much torque at this speed, so my depth of cut is limited by the feed pressure, and I can't get away with more than 1/10 of a millimetre. This makes for a lot of passes, which is fine, but it also means the chips are very thin and long. I assume the chip breaker is just not effective with chips this flexible. I have to stop and clear the tangled chips between each pass. However, even clearing the chips after each pass is not always enough, and eventually this happens. The chips have been pulled behind the chuck, wrapped themselves around the spindle, then been pulled between the backplate and the main bearing. This is going to take a while to clear out. As I put off the messy cleanup job, I thought I'd go back to the mill while the work is still set up. Another important feature of the faceplate are the 3 holes. Darren Radcliffe commented on part 3, letting me know that these are used to locate the centre of the part being machined while adjusting the clamps viewed from behind. I defined the 2 symmetrical holes as the centres of curvature so I could drill pilot holes and use them as anchor points on the rotary table when I come to machine the curved slots. The camera was set up for drilling all 3 holes, but somehow I've lost most of the footage. Instead of a 10-minute video clip, I have a single photograph taken as I started drilling the first hole. Let me know what you think of this video and the series so far, and please like and subscribe if you're interested in seeing more. I'll do the rest of the rough spindle turning off camera. In the next part, I'll be milling the curved slots in the main plate.